All right, so we saw how we could get these E cells, pull them from a table, but remember these are E cells at standard conditions. So generally 25 degrees Celsius, and the most important part, the 1 molar in this case. So what about things that aren't at standard conditions? So we can calculate them, and this is done through the Nernst equation. So you can see the book for the derivation. I'm just going to give you the overall equation, and it's that E cell is equal to the E cell at standard states minus RT over NF times the natural log of Q, where R is your gas constant, your 8.314, T is your temperature, N is your number of moles, and F is the Faraday's constant, that 96,000 something kind of thing. And then you can look at another form of this equation, then that's at 25 degrees Celsius or 298 Kelvin. So when you do that, you can simplify it further into a different equation. And so it's E cell is equal to the E cell at standard states minus this 0.0592 volts. So basically just combining all of these constants into a number over N, which is your number of moles, times the log of Q, log of Q. So just pay attention to these two equations. Right, remember, N here is number of moles. And then Q here is your reaction quotient. And so let's take a look at these example, or an example of something at non-standard states. And one example is a concentration cell. And so in a concentration cell, you have kind of the same thing in both of your half cells, but they're at different concentrations. So let's take a look at an example. And so that's kind of find E cell for solutions of 0.10 molar zinc 2 plus and 0.50 molar zinc 2 plus connected with a zinc electrode or electrodes and a salt bridge at 25 degrees Celsius. So we're at 25 degrees Celsius, so we can go ahead and use this lower equation. Let's go ahead and copy that down here. So E cell equals E cell at standard states minus this 0.0592 volts over N times the log of Q. So think about it, we've got zinc on both sides, and so they're going to have the same cell potentials, and so it doesn't matter which way you subtract them. Overall, this is going to be 0. And then let's take a look at N next. What the heck is the value of N going to be? Well, we're thinking about zinc 2 plus going to zinc solid, and so you can see that's a 2 electron change. And so we're going to plug in 2 there. And then finally, our Q. What is our Q going to be? Well, remember, Q is products over reactants, right? And so which one of these is our products? Which one of these is our reactants, right? We've got 0.1 molar and 0.5 molar. Well, if you think about it, they're both zinc, and so at equilibrium, they should be exactly the same. And so the 0.1 molar should actually see an increase in its concentration, and the 0.5 molar should see a decrease in its concentration to get to the same value. So the 0.1 will be the products, and the 0.5 will be the reactants. So plug that in for Q, plug and chug through this math. And then you finally get an E cell of 0.021 volts. So we can see that this difference in concentration can generate a potential and thus do work. Here's just a picture from one of the books, right? So at standard conditions, they're both going to be 0.1 molar. That's on the left here. And you can see you're generating zero potential, right? It makes sense. You have the same thing on both sides. You're at equilibrium. Nothing's really going to happen. But now we're at non-standard conditions. So we have one that is more concentrated than the other. And so they're going to go until they're the same concentration. And so we can measure a cell potential for that.